Good afternoon, everyone. Welcome to this webinar. This webinar is being organized in the west of Singapore in Nanyang Technological University. The webinar is organized by the NTU College of Engineering, supported by the Energy Market Authority. And the webinar is designed to share knowledge and information to listeners out there to look at how we can navigate through the complexity of technology in this so-called new normal, where technology is affecting us in many ways in our lives, in the industry. We have a number of distinguished speakers. Before I go there, I thought I would share with you a little bit of a perspective. Now, some wisdom from Dilbert. I will leave you a little time to read through the comic. Now, the pointy head boss is using all kinds of technical jargon, but mixing them all together, right? Texting and Skyping and the cloud, and then of course Dilbert solved one of his strange questions by saying that he can store data in a large cloud called the cumulus nimbus cloud. Of course, this is a weather pattern type cloud. Now, here, technical jargon, some people do not understand. Another one. I let you read again a little bit. Now, the cute cartoon here is Dilbert using a headset that translates technical jargon to what actually the person means. Now, this is the situation out there now. Lots of technology, the technological acronyms, words and so on, and that is very confusing. So today, to help us navigate through this complexity of words and jargon, we have two distinguished professors who will join us to do a presentation, and then you will have the opportunity to ask questions of them in the area of digitalisation as well as in power systems. First, Prof. Wen. Now, Prof. Wen is an expert in AI. He's a fellow of the IEEE, and of course, IEEE is the International Standards Committee. He's a professor of computer science and engineering at NTU. He's also Associate Dean of Research at the NTU College of Engineering since 2018, overseeing all research collaboration in the college. In his expertise in AI, he has led many industry-led collaboration and with very many distinguished and reputable industries and companies, of which notably that includes Toshiba and Alibaba. He received his PhD from MIT in 2008 and has published more than 200 papers, many of them have won Best Papers awards. Now, Professor Gui is in a different part of the university, but they are very interlinked in this day and age. He is an expert in the power systems and energy management. Now, his current interests include microgrid energy management systems, energy storage, spinning reserves, frequency regulation, and many exciting smart grid technologies. He was the deputy head of Power Engineering Division from 2008 to 2014. Again, like Prof. Wen, he has secured quite a lot of funding grants in order to do many research projects. He is currently collaborating also with SP Group. With this, maybe I thought I should introduce a little to you about what we do in SP Group. Now, this is a structure of the power grid. We have few companies under the group. ranging from the electricity grid to the gas network to even district cooling. The mission of the SP Group is to provide reliable and efficient energy utility services to enhance the economy and the quality of life. Now, this is a very basic mission. We power the nation, we bring electricity and gas to all homes. But behind this, we are also seizing the opportunities to look at how technologies can impact the grid, the power grid or the gas grid, and how to mitigate against these challenges. At the same time, these technology challenges also provide a lot of opportunities for us to leverage on them to be able to optimize the grid and then also provide better services and opportunities for the customers. I will just go through, before that, this is the electricity market, just to share with the audience. On the top, of course, we are the Energy Market Authority is a regulator, and the market itself is a wholesale market. Generation is produces power every half an hour. The power grid is the connection between the power plants to the consumers. Now, this situation is now the challenge and the opportunities, as I said, by a lot of technologies that are coming in to offer disruptive solutions. What have we been doing? Like, this is a simple diagram to see some of the things that SP Group have been chasing and for various outcomes. At the bottom of the first circle is the network itself. Then the next concentric circle are the transmission and distribution assets, the distributed energy resources, electrification of the transport, which is electric vehicles, then the workforce, digitization, and the customer. So this layer are all the components that can be impacted or impacting the grid. On top of that is actually a digitalization, how to string all these things together. And with that, you can then achieve through various technological components, like online condition monitoring, or creating digital twins, or with DER management, energy storage, creating a digital workspace, operational site management through technology, even reaching the consumers through mobile apps. What do you want to do? You want to achieve greater reliability. You want to be able to integrate DERs and call to the business, improving safety and productivity. And then the other end is, of course, customers are very important, empowering customers through digitalization. We have done quite a few. I just walked through some of the initiatives that are underway. This is not comprehensive, and many of them are still ongoing. And we believe that we need to be on top of technology. We need to pilot, test technology, understand the technologies, so that we can figure out how we can leverage on these technologies to improve the outcomes for the power grid. Here, just an illustration, we are looking at end-to-end solutions. On the bottom, you have digital platforms where we're looking at energy management system, we're looking at energy storage system, and the PVs out there, right? So the pictures there are some of the deployments that we have in PVs, inverters, energy storage system. Then bring it together is a control system, which is the DERM system. Now here, ongoing project, bring them together to be able to see the technologies, see the impact of all the components in the grid, and how to be able to monitor and then integrate them together integrate the disparate elements. So developing end-to-end solutions. Here is a picture of a deployment where we put energy storage system in the depot, in a substation, sorry, and we are looking at piloting how energy storage can actually shave off the peak and therefore defer some capex in terms of in the transmission and distribution network. You can see some of the graphs that we have collected over time. The one in the circle. Now, Going beyond the power grid, we are looking at the customers too, right? How we also can integrate technologies for the customers and eventually even integrate back to the power grid. On the left is the some solar panels on top of Bukit Panjang Community Center. Throughout through the facility, we introduce various technologies, and that one also, the target is to do energy saving. We have deployed within our own substations and depots a number of the solar panels, energy storage system, in order to see what are the kind of things we can do with this technology, including energy saving. In the third column is a commercial deployment in the Tuas Boulevard Yard, where we do PV and ESS monitoring, peak shaving, even load forecasting and shifting. And you can see the solar panels in the picture. This is one of the largest solar panels deployment in Singapore. On Jurong Island, some examples, PV monitoring and reporting to the power systems operator. So visually, just some pictures again. Through the power grid, we are looking at all kinds of technologies, and this is only the beginning, because we think there'll be more and more technologies that will come our way. Each of them present, as I said, opportunities and challenges. We are collaborating with many parties, including NTU, to develop solutions to leverage these technologies, as well as to be able to grow capability within the group. So with that, I will introduce Prof. Wen to carry on the seminar to share with you his thoughts about AI in this new norm. Prof. Wen.
Thanks a lot, Jimmy, for your kind introduction and the sharing of the digital journey at SP. So my name is Yung Kian Wen. I'm the Associate Dean at the College of Engineering and also a professor at the School of Computer Science. In today's talk, I will share some of our latest ideas about digital transformation, in particular focusing on how we can use AI to enable and empower digital transformation journey for our sectors. So actually, digital transformation has become a trend over the last couple of years. So we have talked a lot about, but never has been so much discussion about digital transformation as in the last 4 months due to the COVID-19. As Mr. Henry mentioned in one of his speeches, said COVID-19 has done what many CEOs and CTOs found hard to do: accelerate digitalization. Even when the pandemic ends, the world will be very different. We will enter in a new norm in which digital channels will become the primary and, in some cases, sole customer engagement models, and automated processes will become a primary driver for productivity. In today's talk, I will first attempt to demystify digital transformation and articulate what actually digital transformation meaning to us. And then I will zoom in, look at the main driver for digital transformation. I use AI to enable and empower digital transformation. And finally, I will zoom into one specific area, which is industrial AI for us, how to go through the digital transformation journey. Let me start with the digital transformation. In this part, I will talk about what is actually digital transformation. And then I will also look at what are the successful factors in the term digital transformation. And I will look at how we can strategize our digital transformation effort in our sector. So first, what is digital transformation? In my understanding, digital transformation actually is the destination with 2 intermediate stops: digitization and digitalization. Digitization refers to the process of changing analog information, for example, paper-based process, into digital form to allow computer to store, process, and transmit. After digitization, then we can use and deploy digital technology and information to transform our business operationals. This process is what we call for digitalization. With these two intermediate steps accomplished, we will enter digital transformation, allow us to use digital technology to improve existing business process or models, or even create a total new business models. Here, I want to emphasize that digital transformation can not only just apply to cyberspace, it can be applied to physical space as well, for example, physical operationals and infrastructures. And here is a framework we have come up for us to strategize our digital transformation. In a business, we can capture value in multiple ways. Here I present two ways we can capture values. In the x-axis, business can capture value through the new business to the customers. Or alternatively, in the y-axis, business can capture value in the internal operationals. So therefore, in the left lower corner is the status quo, in which the digitalization does not play a very important role. So in order to capture more value, we can either move up in the internal operations to adopt more digital transformation, or we can in the horizontal axis to adopt more new business with digitalization to capture values. When we move up in the internal operationals, this more referred to digital operational transformation. Specifically, is a way to use digital optimization techniques to improve our operational efficiency. Case in point in this is like we have ERP and CRP applications previously. When we move right in the external value capturing, we can adopt more digitization transformation for us to capture new values in the business from the customer side. One example is when we use search engine to actually help us to allow the content of our website to be more visible or more viewed in the search engine result page. So these are the two ways we can improve the value with digitalization and digital transformation. And the holy grail of digital transformation is on the upper right-hand side corner of the matrix. In this area, we actually propose to use digital transformation not only just increase my internal operation efficiency, but also capture the new values from the customer. An example in this case is the Amazon Web Services. Amazon actually created the most successful cloud infrastructure business out of the improved operation efficiency in the infrastructure, compute, storage, and database, in which they built for the support the e-commerce business, but then they create a totally new value business model out of it. So this is a way for us to strategize our digital transformation. Now let's look at what are the successful characteristics of digital transformation. So first, we firmly believe believe that digital technology will result in substantial and complete industry transformation. And second, we need to have a clear go-to-market strategy in the digital transformation, as well as we need to see some return on investment in our digital effort. And lastly, we should not do this alone. We can leverage on external parties with complementary expertise to support our digital transformation journey. So these are the four successful characteristics we would like to see in the digital transformation. Now let's do a fact-checking based on a survey conducted by the industry. First, whether we have this, noticeably, 2/3 of top management believe that the digital technology will lead to substantial and complete industry transformation. Get checked. And second, whether we have a clear go-to-market strategy for digital transformation. And unfortunately, the senior management had a mixed feeling of this part. They are not sure whether digital strategy are fully deployed yet. And third, have we seen any ROI in your digital effort? And this industry have overall struggling in terms of seeing the ROI for the digital transformation. So we are not there yet. And lastly, can we leverage the external partners for our effort? Actually, the survey found out 71% of top management placing increasing priority on external partnership as a result of a digital transformation. So we do see that the senior management had set the agenda right for collaborations. So putting all this together, we know digital transformation is the ultimate objective or goal we need to reach out. But also we realize that the industry is not fully ready for digital transformation yet. In Singapore, actually, our government is really, in terms of futuristic, we place the digitization as a top priority in our national strategy. Unfortunately, our industry do not have to do this by ourselves alone, by ourselves. Over the years, Singapore government has invested a lot in R&D with public institute and IHLs, and therefore we have built a very solid R&D base for digital transformation. Moving ahead, we encourage the industry working more with our IHLs to embark on this digital transformation journey. So this is a quick summary. And then next I move on to what are the main driving factors for digital transformation. What I believe that AI will play a very important role in digital transformation for our local industry, in particular the power sectors. So actually, digital transformation can happen both in cyberspace and physical space. In both realms, AI actually will be the main driving force or factor for digital transformation. We didn't know the application of AI in. We didn't know business AI as the AI in digital space in their business. For example, we use AI to transform our operations within the organization, for CRM, HR management, finance, and marketing. And we didn't know the industry AI as the AI applied for the physical space operations and the management. Examples like factories, buildings, logistics, and data centers. In both domains, we envision that AI will play a very important role to transform our business in the digital transformation. So actually, also we believe that with these three components of AI, data, hardware, and software, has reached a tipping point for AI to be deployed for our digital transformation. So this is a good opportunity for us to get on the journey of digital transformation, and in particular leverage the latest AI technology. So let's do a fact checking of how we are doing with business AI. One survey found out that 74% of business respond that they connect the AI and the digital initiative together, and this combination has already generated some kind of business impact. This good result has been further supported by another survey conducted by the Forbes to ask the industry to list the top 3 functions where AI can realize its full potential. Actually, these 3 areas are marketing, customer service, and sales. Therefore, we can see at the digital space, business AI has already seen much success and traction in industry today. At the same time, now because my own research in industry application, we do believe there's a world of opportunities in applying digital transformation in the physical space of our business. That's my next subject is look at the one specific area called industry AI. Let me first start by providing you my own definition of industry AI. Actually, industrial AI refers to any application of AI solutions into physical operation or systems, for example, offices, data centers, factories, power plants of an organization. And its main purpose is to help the organization to digitize, optimize, and automate these operations and the system to improve their efficiency and performance. These become more important or more urgent as we've been through this COVID-19 pandemic stage. So actually, let's look at these three factors for AI again, data, hardware, and software. In particular, we see some additional driving forces for us to adopt AI in our physical spaces. First, look at the data. Nowadays, with the pervasive IoT system, collecting data becomes so cheap, and also data can be collected in a very fine granularity. And second, in the hardware side, with the deployment of robotics and intelligent systems and device, we have a better way to automate our physical spaces. And finally, as Jimmy also mentioned, digital twin will play a very important role in future industrial application to actually better represent our physical world in the cyberspace, then create a continuum of physical space and cyberspace in the same platform, so we can manage both of them at the same time. So actually, in industrial systems, actually, we often first need to look at the problems which are visible to us, as well as problems which are invisible to us as the operator. In another way to look at the problems we need to address in physical spaces, problems we're trying to solve. But often cases, they are problems we're trying to avoid in the first places, and which in physical space, we see a lot of this challenge. And these metrics give us a way to look at what the industrial AI can be applied to our physical spaces. Look at the left, the lower corner is the status quo, which we operate nowadays. This can be resolved with a continuous improvement by our quasi solutions. Often case, actually, more important to us as the industry is to look at the problems which are invisible to us. But often case is the problem we're trying to avoid in the first place, because once there's a problem, there's already potential issues. We're trying to avoid this problem even before it happens in the first place. So these are the ultimate goal we want to drive this industrial AI to address in our physical space. For example, in status quo, we're trying to fix a machine when it breaks down. But it will be better if we can avoid this problem in the first place by we can avoid a machine to break down by using predictive maintenance. Like in our Singapore Power, I see an initiative to use condition-based maintenance, try to even prevent the problems to happen. So therefore, we can avoid this problem in the first place. And another way to look at is we want to address the invisible problems which we want to solve. For example, in a manufacturing line, we can use AI to build a complicated relationship between a set of conditions to the optimal production parameters in the manufacturing line. So these kind of things can further improve our productivity and the efficiency in operations. The holy grail of this industrial AI is even before we try to address any problem, in the design stage, our AI can help us to avoid potential issues in the later stage, such as we can solve the problems which are invisible in its nature, but also avoid these problems in the later stage of my physical operations. This is a very good way for us to think about what we want to do in our physical space by enabling AI solutions over there. So actually, through my own experience, I've often been asked, Prof. Win, what are the best ways for me to start an AI project? How do I have a high-level strategy? Then I come up with a framework called PRADA. Then I using the famous movie title, The Devil Wears Prada. I often call my own research the AI wears Prada. And what does PRADA means? Actually, PRADA is a framework for people to strategize the AI journey in the operationals. P stands for platform, especially computation platform for you to deploy your AI solutions. R stands for researchers. As the workforce, you recruit or you are assigned to do this AI project. And the algorithms, what kind of specific algorithm you can develop for your own solutions. And most important is the data. Data is counted as the fuel of this future AI engine. And lastly, often overlooked is that the application. In our industrial AI domain, we are application driven. We first have our problem statement. Then we look at whether we can use AI actually address these problems. As I just explained, for problems which different natures, then depending on the nature of the problem, I can use different AI solutions to help me address those problems. So then I can use this framework to share with you some of the challenges when we're trying to deploy this industrial AI for our digital transformation journey, and also what are the possible ways we can hope overcome these challenges. First, look at the platforms. Actually, the challenge comes from the industrial often involve complex physical systems. And these systems are very different from our digital space. In a digital space, for example, in Netflix, you will not feel a pain when Netflix recommending a long movie for you to watch. But in a power system, if there's a false positive, then the complication could be huge, or the impact could be huge. Any misjudgment and any misalignment will result huge cost and the complication as well. And oftentimes, in order to adopt AI solution, we need to use simulation or a cyberspace solution, hope as to train and testing our AI solution in the first place. So these are the unique challenges we face in industrial AI. And second, let's look at the researchers or the workforce we're going to employ for our industrial AI solutions. And because of the uniqueness of this industrial AI solution, we will require talents with two arms of expertise. First is AI and data science expertise. The other is domain subject expertise. This needs to be worked together, what I call AI plus X. X refers to domain knowledge. And unfortunately or fortunately, there are not so much talent on the market for this purpose. So therefore, as a senior management or project lead, we either recruit this kind of talent or have to upskill my current staff to have this capability. That's why at the university, COE in particular, we have a lot of these skills future training programs. Hope our local economy or hope local business to upskill the existing staff with this technical background in AI and the domain subject. So let's look at the algorithm. If we look at the specific algorithm applied to industrial AI domain, and a lot of times these are heavily regulated in the industry. The algorithm adopt for other domain. When we're trying to push to the industrial AI application phase, we need extensive validation and verification before we can adopt to our physical spaces, because of the stake is too high, and often these infrastructures are mission critical. And this is one aspect. The other aspect, we need more sophisticated algorithms in the first place. That's there's another funny picture here. Often we thought it's very easy, but actually when you push this sophisticated algorithm from AI to an industry application, we realize there's a lot of challenges along the way as well. And oftentimes we start with the big help and vision we'll do something great, but end up we have to spend a lot of effort trying to push the AI solution in the industry domain. I can use an example in which is in my own research. Around 2012, I tried to propose to use AI to do the cooling optimization for data center. In 2012, no one actually believed that. And it's very difficult for us. We have developed a really good algorithm, but it's really difficult for us to convince someone to adopt this solution in the data center physical management. Not until 2017, and after 5 years, people start to be more receptive to these new ideas. After we've done a lot of validation and in the digital domain, in the physical domain, people start to appreciate these kind of solutions. And talk about the data in the physical application or physical domain. Our data availability will become an issue because of the cost, privacy, and quality issue. And we don't have a lot of data, although we think we have a lot of data in the physical system, but oftentimes this data quality is not good enough. And also the labeling of this data requires a lot of effort to label them for training purposes. So oftentimes we have to use digital twin to generally self-label the data for me to train my AI algorithms. And this is a new paradigm. Actually, digital twin can find a good application in application domain. And even more important, in the physical space compared to our digital space, how am I going to train my machine learning model to taking care of those red black swan events, like part of the system fails? For example, using the airplane industry as an example, we will not be able to fly for a pilot to fly airplane and to crash on the ground just to get the data. We will not be able to do so. How should I be able to collect data for these black swan events for me to train my machine learning? Again, digital twin potentially could be applied for this purpose as well. So these are new kind of ideas which has not been implemented and deployed in the digital domain. And I would encourage our industry also look at this aspect as well. And last, the application. So actually, because we are dealing with the heavy industry application, the cost of this usually huge and the stake is high. Oftentimes, it involves a high cost should the algorithm fails or there's any changes. So this is something we need to think through even before we start our digital transformation journey with AI. How should I be able to manage the cost? So with that, all these challenges to deploy industry AI for digital transformation in our physical space, and industry AI do present a lot of values to us. So here are what I can summarize, at least 4 value propositions to the industry application with AI solutions, ranging from the generate new revenues, reduce our cost, and manage risk, as well as to enhance the productivity and efficiencies in the process. So with that, I'd like to conclude my talk with help you to have a good understanding of digital transformation, as well as how we can use AI to enable and empower digital transformation journey along the way. And hope this 20 minutes presentation will excite you in this new domain so you can start to plan and think about what you can do with your digital transformation in your own sector. So with that, I thank all of you for your attention, and I'd like to pass the floor to Professor Gui for he to share focus on the topic of his presentation, digitalization of the power sector. Professor Gui.
Good afternoon. Thank you, Jimmy, for the introduction, and also thanks to Professor Wang for the opportunity to speak this afternoon. So my name is Gui Huibing from the School of EEE, NTU. Today, I have chosen the topic, digitization of power sector, and this goal align very well with the government promoting the digital economy. So my talk this afternoon encompasses 7 items. Basically, I'm trying to introduce the electricity supply industry in Singapore. As you are all aware, it comprises generators, grid. Grid, we are referring to transmission lines and distribution system. And then finally, we have the consumer at the end. So in between, I also introduce wholesale electricity market, because this is something that is very important, where Singapore, we buy and sell electricity through electricity market. And then I also wanted to talk about the assets health management of distribution grid, because this is getting very important nowadays. And then after that, I will conclude with my talk. So that's basically the outline of today's talk. So if you look at it carefully, our supply industry comprises 3 big items: generation, grid, and consumption. But you can see over the years, things have changed. Nowadays, if a Genco wants to compete into selling electricity, it better have a very efficient generator. If not, it's very difficult to go in, because the market is very competitive. So we are talking about very high efficient generator. Now, long gone with the days where our generator can only have 20% or 30% efficiency. But today, we can get easily 40%, 50% due to the new technology that has been introduced. So the grid side also has gone through a lot of changes, mainly with the IoT, the ICT that have been introduced. And what is more important, I think in Singapore, we just completed the construction of the tunnels. We have a north-south tunnel and an east-west tunnel comprising a total of 35 kilometers. Nowadays, we don't want to continue and dig the ground and then bury our cable. So you can actually walk in the tunnel, and then you can see the cables just next to you. So you can actually introduce new cables. Of course, with the existing cable, we are not touching anything, but new cables, we can do something about it. Yeah, and I see that a lot of changes are actually happening in the consumer end. And you can see too that in 2019, our Singapore achieved a full retail contestability of an electricity market. What it means is a household consumer can choose the supplier as he or she wishes. And nowadays, we have many rooftop PV, and PV also install many what we call floating PV. And today, our PV installation is still very small compared to the West. We have only 350 megawatt peak. It comprises about 5% of our peak demand. Our peak demand will be somewhere around 7,000. But in reality, we are not actually achieving 5% because PV doesn't generate electricity all the time, only for a short period of maybe 8 hours or 10 hours. And you will see in the next few years, a lot more energy storage will be introduced. And this will help to address the PV intermittency and variable issue. And then you will see more charging stations for the EV will be installed. And then due to this distributed energy resources, we expect that some consumer will get converted in prosumer. What it means is producing electricity as well as consuming electricity. So to see the two, what we call the top diagram and the bottom diagram, you see that distributing grid actually have bidirection, which means it can actually flow either way. So how will this digitalization of power sector help Singapore? I hope I will be able to answer this question in this short presentation. So I think this gives you a kind of brief overview that our electricity generation primarily comes from natural gas. We import what we call liquefied natural LNG from various parts of the world. And so we're using primary gas to produce electricity. And then our PV, solar PV accounts for, and biomass, 2.9%, other fuels, less than 2%. So our generation side, we have a CCGT, combined cycle gas turbine, and we have cogen and trigen. What it means is we not only produce electricity, we also produce steam for the industry. We also convert it for cooling purposes. So we have talked about, I think Professor Wang and also Jimmy have spoken about digital twins. So you can see that we are not just talking about a single domain. They're producing electricity. We are talking about you need to know electrical side, you need to know the thermal side, you also need to know the chemical side. So it's important that each of us don't work on a single particular domain. We should all work together. If we all work together, we can actually achieve better efficiency. And this digital twin will come in handy. It allows you to actually combine all this domain knowledge to what we call a physical modeling of all this. And then you can actually do a simulation rather than you play on the real system. And then you can actually derive more efficiency from there. And COMSOL will be a software, commercial software, that allows you to do this multi-physics simulation. And this is what this diagram is trying to tell you. Now, electricity generation comprises many parts. At the power plant, you can see at the bottom, somewhere in the middle, there's this combustion of natural gas, and then heat will be produced. And then with the heat produced, we will have to be able to generate the steam. And the steam will come in to actually drive the steam turbine where we located, I think, number 3 there. And this, what we call the steam will act on the blades of the steam turbine, will then drive the generator. And when electricity is generated, then it will be actually step up. Electricity usually generated not at a very high voltage. It's usually about 4 kV to about maybe 20 odd kV, but we need to raise it to a higher voltage for better transmission to actually minimize the losses. And that will be going through a step-up transformer. So you can see from the power plant, there are actually many parts that we need to worry, and that includes even electrostatic precipitator in the smokestack. So anything of this can actually fail. And when components fail, it actually gives rise to a lot of headache to the electricity supply. So some of these may lead to a complete generation outage at the power plant, while others may lead to actually a duration of the generation capacity. That means, for example, one of the pumps not working. It doesn't mean that it will actually stop the electricity production. It can still continue, but maybe at a lower capacity. Because pump is not working, that means you cannot actually circulate the water. You can see that once in a while, Singapore, even though our electricity supply is quite robust, and all the time we supply electricity, but at times, even in 2018, we have big problem there. It's not just one single generator outage. We have 2. As you probably are aware, our power system is not designed based on N-2 concept. Rather, it's based on N-1. What it means is you only allow one generator outage. Then now some of you may ask, why do you don't want to design a system that can withstand N-2? Oh yes, we can design, but it will come with a cost. And that cost means you have to have more spin reserve. Spin reserve is what we call standby power. It's something that is still kind of spinning, but it's ready to go. It's online, but this comes with a cost because you need to actually bring in more generator in order to provide additional protection. Now, whenever you have this type of thing, and in the 2018 event, we lost many customers. The good thing is that outage happened during the morning, very early in the morning, somewhere around 1 to 2 a.m. And it's the time where you should be sleeping. So luckily, then when that happened, it did not actually cause a lot of losses in the sense of business losses, because at that time it was midnight. And then you can see that how Singapore Power restored the supply. Within 38 minutes, somewhere around less than 40 minutes, the power is back. So actually before 2 a.m., every household gets back its power. And for that, I must give my hats off to Singapore Power Control Center personnel. They are able to actually get the power back in a very short duration. Now, it's not wrong for the GENCO to actually make the system, their power plant more efficient, but what is important is we also need to put attention on the asset performance, because assets are things that are helping us to generate electricity. So we should also pay some attention on maintenance service. So these are what I call APM and MSM, need to be actually coordinated and make sure that we have all our assets perform very well and then producing electricity. So the purpose of APM is to optimize asset strategies, improve the machine and component health, enhance the reliability through performance management. So I think if we can use this physics-based type of analytics and then combine with AI algorithm, machine learning algorithm, then we will be able to predict the failure of it's a kind of probabilistic base. So we will be able to predict the failure in the future. And then we will know if the failures are too high in the future, then perhaps we should do some component replacement and start to get the system in good shape again. So the idea is we want to be able to predict the remaining useful life of the component. Now, if we are able to integrate APM with the condition-based type of maintenance scheme, then we can unlock our productivity and make our power plant very, efficient and operate in a very tip-top condition. So APM actually avoid forced outage or minimize the forced outage, and then it will actually promote scheduled outages. So you don't have to actually stock up many spare parts, and then you don't have to actually do a frequent inspection. And this will definitely help to drive down the cost. So I think I've seen many organizations, they do maintenance manually and then do a manual record keeping. And this actually is not very efficient to go forward. So it's important that we try to make this engaged digital maintenance tool to help to maintain and then keep a good record of all this. I give you a few examples. For example, you can use a robotic inspection of the turbine blade by using a laser scans. We can actually look at the blades of the turbine, whether we have a hairline crack, and then from there, we will be able to examine it's a good time to actually do a replacement of blades, turbine blades. And then we can also use the drones to reach very unreachable area like smokestacks. And then these drones will be equipped with camera, high-resolution camera, and then you can take pictures of the boilers, inside the boiler, or even in the smokestack. And then we can actually compare the images from the images taken a few months ago, and then to see how the component have aged. And then based on that, we can actually determine whether to replace the component or not. So these are very useful schemes that will help the power plant to maintain the component at a tip-top condition, and then to actually prevent outages. And that is the motivation of this work. Singapore, we have what we call the wholesale electricity market. And you can see that there are many players. We have the Genco, we have SP Power Grid, which is the Greek operator for both the transmission line and the distribution line. And then we have a consumer that will receive the electricity. On one hand, on the left, we have electricity flowing to the consumer from the power plant. On the right-hand side, you will see the money changing hand from the consumer back to the Genco. So we have this electricity market where the buyer and seller will come in. And then we have even the EMA, which is operating the power system control center, especially on the energy management system. So our electricity market actually started way back in 2003. And then at that time, we have a vesting contract. And then if I'm not wrong, currently we also have vesting contract. And vesting contract is something that we want to actually cut down this market power. And open electricity market is already in the operation. It started in 2018, if I'm not wrong. Actually, I was among the first few to actually sign in for the OEM. In fact, I just finished my first contract of 2 years, and now I'm actually going to the second contract. If you have signed for this, I'm sure that you can save easily, maybe 20% of the electricity bill. So there are many players there. The Genco, they all try to maximize their profit and minimize their risk, and so will be the retailers. So these are the one that try to make a lot of money out of the market, but EMC will be actually at our side, is trying to maximize the benefit and lower the electricity rate if possible. So we have nodal prices throughout the entire power system, and the Genco will actually be paid according to those nodal prices. And these nodal prices are price signals that will tell you whether the system has congestion, and then whether it will be a good time to actually build power plant in that neighborhood. That's basically what nodal prices are all about. Now, in Singapore, if I may, I actually classified the entire power system in 3 layers. So we have transmission and sub-transmission voltage level, and we have 400 kV, 230 kV, and 66 kV. And then we have a distribution power grid that comprises mostly 22 kV substation and 6.6 kV substation. And then most of our household consumer are actually at the 0.4 kV three-phase or 240 volt single phase. So for each voltage level kind of a category, we have an EMS that is actually managed by the Energy Market Authority of Singapore. And then we have a DMS at the Ayer Rajah Power System Control Center, and this is managed by SP Power Group. And then I think we heard about Jimmy talking about DERMS, which is an ongoing research project between the SP Power Group and the NTU. And I think all the world, you have heard about microgrid. So the microgrid EMS and the DERMS are something that will happen in the future. In fact, some of the countries already have this system running. So I think when we look at what is important to the consumer is the service quality. The service quality represents something that is important because we are talking about constant voltage and constant frequency. This is what we are trying to achieve our KPI, especially for the SP Power Group, because this is what we call the quality of our electricity supply. And how do you achieve that? Of course, to achieve a very constant voltage and constant frequency, you need to have secure operation. Secure operation means you have to have a lot of spin reserve in the system, or you build redundant transmission lines, and then you have a double circuit, and that will ensure that operation will be very secure. But when you talk about secure operation, it means high cost, because this This is something that you need to put in order to achieve. So on the other hand, the consumer says that no, I'm not going to pay such a high cost. So these two are actually contradicting factors. Somehow we need to strike the balance between the two. Yeah. And I think the best way to actually handle this is by what we call the energy management system. You get a lot of analog or digital data from the field, and this will be transmitted and then presented to the operator. Then the operator will take a look of what the entire status of the power system. And normally, the operator is only monitor, and very seldom they need to do control. But once in a while, we need to actually do some control in terms of raising the voltage or lowering the voltage. And we also have what we call undersea cable that is connected to Malaysia TNB system. This is normally not much energy transaction over there. It's actually free-flowing type of tie lines, and we have about 400 megawatt undersea type of cable system there. Yeah. So the way it happens is we are doing a control at a very fast rate. For example, our AGC run at 2 to 4 seconds. So it's not possible for human operator to do it. So the best way is to use a computer. And that computer is what we call the EMS at the Power System Control Center. So this is an overview of what EMS is all about. I actually split the software module that you normally will find EMS in about 4 categories. In the center, we have a network application that comprises model update, state estimation, security assessment, and power flow, including the network sensitivity. Network sensitivity will be the one that actually gives you the loss factor, penalty factor. Whereas on the left, you will see the AGC. AGC is the one that is doing the controlling on the generator and is running at 2 to 4 second execution velocity. And then at the bottom, you will see the forecast and scheduling function. And nowadays, in Singapore context, we don't run unit commitment. This has been pushed to the GENCO. And in fact, GENCO is doing what we call the self-commitment. And on the right, you will see a DTS, Dispatcher Training Simulator. Basically, this is the one that actually trains the new hire. Whenever you have a new person reported to work at the control center, you probably will actually lead him and teach him and you have an experienced teacher teaching a new hire how to actually handle this EMS, how do you operate. And you can actually introduce a very complex scenario in which you don't have a chance to operate, but with the DTS, you can introduce any outages and test his response, his alertness, how to actually get the system back. So we actually at NTU, Professor Wang Pen and I are teaching this EE6510, Power System Operation and Planning. And if you are interested in this, we can actually talk to you over the whole semester. Yeah. Okay, so you will see from here that our current EMS is not very ideal. What we want is we want a self-healing grid. It means if in the future we have outages, I want this, everything restored, and then back to normal. And then and the best is don't get human being involved, because human being takes a long time to think. We want the computer that is equipped with AI, and then it knows what it needs to do. In fact, if you look at EMS now, it actually has some feature that not quite there yet. At least we have predictive function. We are able to do forecasting very well. But what we are lacking is we don't have a look ahead feature. We must be able to look before things happen. Like, for example, you are driving your system close to collapse. Maybe at that time, we must have a few scenarios that will guide the system. In case we get to this, maybe we should drop some load or maybe swap some load to other places. So we need to have prescriptive type of features in our EMS. And more importantly, it must be a closed loop. And in fact, we have done quite a lot of closed-loop system. We have a closed-loop security assessment system. We also have an AGC that's closed loop. So I think we are there, but not quite there yet. So we need to actually invest more in the AI, and hopefully with this, we should be able to get to a better system. Now we want to move to the part that is controlled by Singapore Power, and that is DMS. If you go to the control center, there will be two systems there. One is the EMS, the other one is DMS. Now, DMS doesn't have all the features that EMS has. It has mostly the network function, but it doesn't have a dispatch function. It doesn't have scheduling function. Then I think the important thing that's for the DMS is to be able to handle so many substations out in the distribution system. And in Singapore, we really have more than 10K of substations. And because of so many substations involved, the power system restoration become a complex issue. We need to have an AI-based type of power system in order to restore the power system whenever outages occur. So based on the circuit breaker opening timing and the sequence and the opening of the real circuit breaker, we will be able to identify where the location of the fault is. And then once you know the location of the fault, you should be able to isolate the fault, and then power restoration can happen. Now, the outage usually must be resolved within 2 hours. That is the standard set by EMA. And then we talk about system average interruption duration index. In Singapore, we are among the best, at least in Asia, if not the world. So we are talking about less than 1 minute per year per customer. And in fact, EMA wanted to impose even much stringent than that. Yeah. So we have engaged, SP has engaged the OMS that was introduced in 2014 to lower the response time of the outage. So you want to actually restore the supply back quickly. OMS is all linked to the customer information at the enterprise business system. And what it means is sometimes the household consumer forgot to pay bill or maybe default on paying bill. Then I think this is nothing that we want to restore the power supply back for the consumer. So I think if it's a fault due to the cable, then I think we need to restore. So MS is also linked to the electricity mapping system, so we will be able to identify where the cable is when we carry out the power restoration. So I think this gives you the detail how the OMS will work. Whenever the fault location is received by OMS at the electricity supply center, then they will start dispatching staff to the site. And in Singapore, we have 5 different sites so that we will dispatch a the technician to go to the site to restore, depending on the proximity of the site. Yeah. And once officers are dispatched at the site, then they will be able to check based on the help of the OMS. There is no need to actually check all the overground box, but just look at the OMS recommendation because it has a prediction engine, and the engine will tell you which cable has problem and which overground box you need to look into. And OMS has been proven to actually cut down the response by saving 20% of the time. So in that sense, it's very productive. And then OMS can now work with a smart meter because if your officer is carrying a tablet, is able to, at the site, will be able to know whether which particular household has electricity supply because they talk. The meter talk among themselves, and then this information will relay to the tablet, and then the officer at the site will be able to locate where exactly which household do not get electricity. So in that sense, we can actually restore the supply quickly. All right, the next topic that is very important nowadays for Singapore Power is about the asset health management. because we're dealing with 12K substation throughout the entire distribution system. And this is an enormous number. If you were talking about substation having, say, 100 components, then you are talking about over 1 million type of component you need to worry. And this component can fail. So ideally, we want to have online condition monitoring. If you have online condition monitoring, you can do monitoring on the transformer, on the switchgear, on the cable. So we don't have to actually dispatch technician going to the substation because if you do that, it's very costly. And then how often do you want to actually check on the substation, the switchgear? So I think the manual inspection is not the way to go because in between, you don't send people there, then how do you actually check on the air system? So cost is an issue because you are not multiplied by 1. You're multiplied by 12,000. So some component you can save. For example, software can be duplicated, but a lot of hardware devices you cannot duplicate. You need to actually produce accordingly. You have to size up. So we have a front-end system, which is at a substation, and there is a picture color in blue. So we have different parts, the sensor, data acquisition, data processing, and communication devices that will communicate with the back-end system, and the back-end will be at the headquarters. So it will have the AI engine, machine learning, then these two will talk. Sensor, we can have many things: temperature, humidity, electromagnetic, acoustic, and electromagnetic acoustic transducer. So all these are based on machine learning, AI algorithm, and then based on this training, using the data that we have collected, we can train and then be able to identify where the type of fault is, the location of the fault is. And then we can engage pattern recognition clustering technique, and then the data collected from the online system can be used for component degradation studies. And that will help us to actually predict our current or future failure rate. And what is important is we want to be able to know for a particular component how long the remaining useful life, when will be the time to actually replace. So this will help us in terms of component renewal and so on. So the goal is to balance the investment cost and liability, and that will actually be the work of asset health management. So I'm almost coming to the end. We have many changes that occur in the LV side, and according to MTI, that is based on the SIL 2019, Minister Chan has said that we are going to deploy 2,000 megawatt peak of solar PV by 2030. And then we have 200 megawatt of battery storage solution beyond 2025. So I think it's good to combine the PV and the storage together because they will actually make the PV system controllable. And this, in the future, when we have intermittent market, it will also come in very handy for that aspect. Now, Singapore, I think our Deputy Prime Minister, Minister Heng, has already said that we are going to phase out the internal combustion engine very soon by 2040. So we are going to have more charging stations installed by 2030. And the EV buyer can expect actually some saving in the cost. We know that nowadays battery is still very expensive, but we believe that this technology, the lithium battery technology, the price will come down just like what is happening to the PV 10 years ago. At that time, it was very expensive to own. NTU, we already installed 5 megawatt of PV, and our president of NTU has said that we are going to install another 4.98 or close to 10 megawatt, but not exactly 10 megawatt, because if it becomes more than 10 megawatt, then you have to have another license. Yeah. So this is among the second or third last slide that I have. Basically, I see that blockchain is coming, and it will encourage and buying and selling of peer-to-peer energy trading. So you can have EV also connected to this system, and then you have buying and selling of solar PV, and even smart buildings, grid storage can also go through this peer-to-peer energy trading. So this gives you some idea. I think Professor Wang has actually touched on this. Basically, we have a smart contract between the buyer and seller, and this is based on distributed ledger technology. And then you have, at one hand, money change hand to the seller from the buyer flows to the seller, and then the electricity will go to the buyer. So I think the blockchain technology cannot solve everything. It only allows you to do buying and selling. You still need to actually look into the power system, the constraint, how do you handle the voltage, how do you handle the frequency, and that's where the power engineer will come in. So at NTU, we're actually looking at it in a positive way. We look at there are so many changes, there are so many opportunities. So this actually will be good for our researchers and the programmers to come in to actually help to solve the challenging problem faced by the power industry. We have in our lab the microgrid. We have OPA-RT real-time digital simulator that allows you to actually design the controller. We can even look into the system-wide type of stability, whether is it dynamics stability issue or transient stability. We can do this type of simulation using the real-time digital simulator. So we have a microgrid setup. We have many items in the lab. We have firewall system. We have a solid-state transformer. And the lab actually has completed many projects. And we have 3 more projects that are currently going. And we use LabVIEW system and MATLAB working with games. And it actually allows you to simulate the real system in a software means. But we can also test the hardware controller. This is what we call rapid prototyping, and things will be going through very fast if you go through this, what we call the real-time digital simulator. So here's my conclusion. Basically, I cover many changes in the, what we call distributed grid, particularly the EV will introduce PV and battery system. And more importantly, I see that perhaps the blockchain is coming. This is for the, what we call the peer-to-peer energy trading. And I see that maintaining asset is a very important issue across the power sector because we don't want to face outages. And then I see that maybe self-healing grid is very important for our digital economy. And SPOMS has actually done a good job. And then we can actually incorporate even more enhancement for it to go even better. So I will just conclude at this time. Now, I was told if you have any questions, you can actually send in, and then we will try our best to answer. Thank you very much.
For a very comprehensive and fairly detailed presentation about both digitization and secondly digitization and digitalisation for the energy sector. At least now I know if we talk about PRADA, we have to refer to Prof. Wen, and if we talk about LV, this Prof. Gui is the person to go to. And for those who don't get what LV is low voltage, not quite Louis Vuitton, but PRADA, LV. We have time for a few questions. So maybe I'll take some questions from that's been sent. For Prof. Wen, there's a question here to Prof. Wen. What are the coming areas that you think AI will play a bigger part in the energy sector? AI in the energy sector.
Sure. So that's a good question. When we talk about AI, we always talk about what are the application scenarios, because the success of adoption of AI highly depends on the application domain. So actually, in I don't know too much about the power energy sector, that details of technology, but I can think in a high level in three application areas one can use AI. First is what we call prescriptive applications. Based, we try to use AI to understand what the power system is about. That's called prescriptive AI. Second area is called prescriptive AI. Use AI to decide how do I operate and running my power systems in a more efficient manner. That's second category is called prescriptive AI. The third part, third application domain is what I call predictive AI. Especially based on AI techniques, I should be able to predict what may happen to my power system should I take in certain action or certain command sent to my power system. So these three areas, the prescriptive, prescriptive, predictive, these all put together, we can have a very comprehensive coverage in terms of using AI for power systems. And someone may ask, now how about my diagnostic functions? That's put under the prescriptive AI.
Yes.
So these are the three areas in a very high level because my own research is more in AI, but then in a high level we can think about maybe
Three categories. Yes.
I can work with
Prof.
Gui.
Gui can mention it. In fact, your presentation you mentioned some areas, but can you just highlight which are the areas that has the most potential as far as AI application in the near term, especially?
Yeah, thank you, Jimmy. So I look at this question. We really have a lot of application in the AI. So I mentioned about power plant. You can actually use the AI for assets management, and you can also use the same idea for the conditioning monitoring of our power component in the distribution grid. More importantly, I just attended the PES general meeting, and it's a virtual conference. It's still going on until today. So I think if you look at it carefully, then a lot of application. One of them, for example, we have voltage issue for distribution grid. Sometimes you may be able to experience very low voltage or very high voltage, especially when the PV, you get a lot of sunshine and the voltage will rise. But we cannot allow this to happen because the voltage must actually work in a certain limit. So I think using AI, we can train our system, and then this will kind of look ahead and adjust it accordingly. So AI will be a very great application for this area. Voltage control is part of our KPI. We need to actually keep our voltage constant, not only just frequency. So it's a very important area to actually work looking into.
Thank you. In fact, another question is linked to what you described, which I also can add on. The question is, given the mention on digital twin, does SP plan to deploy digital twin and for what functions? So this one, agree with you. One, very good potential for having a digital twin and online digital twin and hopefully also real time, right? Is in the sensing of the condition of assets, especially critical assets. Having the real time IoT transfer information all the way to backend, even to the front at the local substation level is an opportunity. So digital twin, but in condition monitoring and what is called asset health analytics. I think that's your view about just when we talk about AI, AI applying onto condition monitoring. Here there is another question for Prof. Gui. What are the frontier digitalization technologies that can look forward, that we can look forward to, that can raise the energy efficiency in the power sector? So this is about energy efficiency.
Yeah, I have actually briefly touched on this. So we have actually electricity generation at power plant. So in the past, we actually waste a lot of our natural resources, because when we generate electricity, a lot of heat is generated, and we have only maybe capture about 20% for electricity, and the rest are all wasted to the environment. And nowadays we can do better, but I believe that in the future we can actually examine the various part of the generation components, and then look at the thermal aspect, the chemical aspect, the electricity aspect, and see how these different domain knowledge can work together. And I have actually briefly touched on it, that perhaps we can use these multi-physics type of simulation to examine how this can help us to get to a next higher level. Because wasting natural resources is just not good for mankind, because our oil eventually will be depleted very soon. So we have to do something about it. Yeah. So this will be a good area to actually look into. So of course we can actually apply the same concept for doing stability analysis to see how we can use the software means to do dynamic security assessment type of thing. So we don't want to face outages, because outages, when it happens, it actually costs a lot of money. So we need to actually get prepared, especially with the penetration of PV expected to increase from now to 2030, even higher and higher. Yeah.
Prof. Kwek, can I chip into one follow-up question before we take one more question and we can call it a day? Now, you say energy efficiency. When you say it, you refer to the power plant, right? From the older the generation technologies to now CCGT, and then using AI in various aspects to improve the energy efficiency. Now, in just across the behind the meter, and that side energy efficiency is used in a different way, right? The building efficiency, air conditioning, and so on, right? So when you think, do you think there's opportunity to integrate the entire system all the way from the customer side to the grid side, in order to then have a total system? And when we say energy efficiency, it's no longer about power supply. It is actually an entire system where you net reduce the amount of energy to fulfill from generation all the way to the customer. Net use of carbon emissions is much less. You see this as a very near-term possibility.
Yes, I think increasingly, I think even at a household, the small little thing that the consumer can do is to replace their tungsten type of light bulb with maybe energy saving light bulb. So I think this has been done across. In fact, our EMB or the government agency encourage people to do this more often. So I see that there are actually small little things that consumer can actually pick up, and we can actually look for air condition, and they give you some symbol, 4 tick, 3 tick, and then you know what to buy. And all this in the future, like we mentioned about REC, Renewable Energy Certificate, which SP is also promoting. We will try to actually promote green energy, where we will use a lot more PV energy if possible. So this is the direction all over the world people are moving. Yeah.
Yeah. So actually, maybe I can also add on that, since I'm mostly working on the demand side rather than generation side. Actually, in the demand side, the energy efficiency also a very important aspect. Just using my own research, data center. Data center is a huge energy consumer. Roughly cost about 7% of all the electricity consumed in Singapore right now, and the energy efficiency in data center right now is normally measured in the metrics called power utility efficiency, PUE. It's defined as the total power consumption divided by the IT power consumption, as close as one as possible. 2 years ago, we did a survey in Singapore. National standard is 2.1, which is much higher than the international standard because of our weather is hot and humid. So there's a lot of room for us to improve in that aspect, to improve the energy efficiency of the demand side. So actually, AI plays a very important role in that aspect. We have done researches in building management, in data center management, trying to improve the overall efficiency of the energy. So moving this ahead, a little bit ahead, maybe a little bit long term, look at in our infrastructure, used to be infrastructure is physical space. Now with software come into place, a lot of the systems are managed and controlled by software. We are looking at maybe 5 to 10 years, it's possible to have software-defined infrastructure. It means have more intelligence for us to, in real time, as you mentioned, to reconfigure the system to target the application in a very nimble way, rather than have a static configuration for a long time. So this is some concept in coming from IT domain, trying to reach out to the traditional infrastructure industry. So actually something we call software-defined infrastructure.
Yeah.
Maybe that's something SP your university, we have a lot of expertise in this aspect.
Yeah. Limited by the power systems themselves, right? But software-defined solutions has moved, right? It used to be software-defined radios, then now in the telecoms industry, you have software-defined
Computing.
the sense of bandwidth of demand and
Yeah.
so on. Yes. So maybe I just add on to this thing about energy efficiency and the demand side and the supply side, and share something that we have done in the SP group. So in my previous position, I was actually the CEO of Singapore District Cooling. Now, there we use quite a bit of electricity in the Marina Bay, and if you know the Marina Bay, we have the world's largest underground district cooling network, right? And we have one of the largest thermal storage system. And what is a thermal storage? You store the cold energy or cold water in order to, instead of producing the cold water as you need, you store it in a huge tank, which is and keep it in ice. And then when you need to, you produce the chilled water by melting the ice. So roughly this is the concept. Now, so on a day-to-day basis, huge amount of electricity is used to produce air conditioning, and then you say similar to data center. And data center is actually used mainly for cooling, right?
Yeah.
Now, the thermal storage center, thermal storage itself is actually in reality a huge battery, storing energy, but the energy is not quite electricity energy, electrical energy. It actually is in thermal energy. Now, we did a simple demonstration together with the EMA, where we linked the system to conceptually an electrical system, where in a situation where there is intermittency of solar panels, right? When the sun goes down or there's a cloud covering it, what you need is either, typically for the supply side, we typically think of injecting electricity through energy storage system. On that pilot, we withdrew energy by shutting down the chillers and then producing the chilled water through the melting of the ice. So in that particular application, you end up balancing the grid. So instead of injecting power, you take away. So you still balance, but at a lower consumption pattern. Now, that concept, I think that has a lot of opportunity for self-healing, because you can actually integrate, if there are many thermal storage systems across the whole country with district cooling implementation, and all of them linked to, say, the power grid, right? When the intermittency happens, you can start to automatically using AI potentially shut down the chillers, and therefore still balance the grid, right? So the idea of self-healing is even more possible if you look beyond simply the supply side. You look at how to use the demand side. And Prof. also does something about taking off power using data center, right?
Yeah.
So that was quite a clever idea too. Now maybe with this, we just have one last question. The question is very technical. It's for Prof. You may want to read this.
Sure.
You read this.
Okay. Can numerical data-driven AI, for example, AI algorithms alone be sufficient for predictive and prescribed AI in industrial AI applications, or are they to be coupled with image recognition techniques and advanced techniques as well? Oh, that's a very technical question. This is actually I didn't,
Somebody who knows.
Yeah, somebody who has a technical background.
technical.
So this is actually referred to a very emerging way of doing AI is called multimodality. So data come with different modality. You could come with the text, you could come with image, you could come with video, you could come with the time sequence. So we used to believe we use single modality data for AI. Now actually the industry consensus was to use multimodality data for machine learning algorithm training. So that's right to the point. Actually, right now most of our research we use multimodality data and further improve the performance. The good thing about using multimodality data is two data modalities may have nothing to do with each other, but working together they can create magic. That's actually is the beauty about using data-driven approach rather than using model-based approach. Let me try to use an example. We will talk about digital twin based on multi-physics simulation. This is based on our understanding of the physical world. We use multi-physics simulation. Actually, there's also another way to look at the digital twin. We can generate the digital twin using multimodality data. Just purely based on data, not using any physical model. The pure data generate the neural network trying to approximate the physical world. And one example is latest GPT-3, which is a machine learning model capture all the human knowledge online. They use multimodality data, image, text, and all this. Now everyone believes this GPT-3 can actually pass the Turing test. So this kind of the idea, actually use multimodality data, that's exactly the right approach we want to use even in industry applications.
That's good. At least you are able to answer a technical question to a person who's probably want to know some technical answers. In fact, just referring back to the cartoon earlier in the beginning, right? I think for some of us, you need the earphone to be able to translate the technical terms to what we understand conceptually. With that, I think I want to thank Prof. Wen and Prof. Gui for quite an interesting presentation that clarify both digitalization and application of the digital technologies into the energy sector. One thing I take away is that now we have a PRADA and an LV, and somebody maybe in the future will have a Gucci, right? So the technology continues to evolve, and I'm sure there'll be new concepts and new opportunities. Again, the power grid will definitely, we SP as a group will continue to look at technologies and work with the partners that to understand the technologies better. So thank you very much. Thank you everybody for joining us today. I hope we can have more opportunities to have webinars like this. Thank you very much.